All right, so now this module, we're going to define calorimetry, and we're going to focus on constant volume. So measuring our internal energy at constant volume using a bomb calorimeter. There will be another module to talk about the coffee cup calorimeter. So first, let's define calorimetry. So calorimetry is the method. It's the method to determine the exchange of heat between the system and surroundings by measuring temperature changes. Now, hopefully, you guys are still taking notes. You have the handouts. So hopefully you learn better if you actually write as well. It sticks better. Okay, so like I said before, there's going to be two methods. Well, we're taking a look at constant volume calorimetry. This is our bomb calorimeter at constant volume. Now, under constant pressure calorimetry, this is where we're going to take a look at our coffee cup example. So this is our coffee cup calorimeter. So again, we're going to be focusing on our bomb calorimeter. Now, here, what we want to focus on is that for our bomb calorimeter, it's going to be at a constant volume. And this is used for combustion reactions. Okay, so these are our combustion reactions. And to find our energy, we're going to force all of our energy change in a reaction to manifest as heat and not work. Heat and not work. Well, how are we going to do that? Well, what does that mean? So let's go back to our formula. Our internal energy equals our heat plus work formula. Well, we know that work, the definition or the formula for that would be minus P external times delta V. And here, this delta V, we've said it's a constant volume. If it's a constant volume, that means that's going to be 0. But we're going to want to plug in this expression into W. So delta E equals Q minus P delta V. Now we said it's constant volume, so that's going to be 0. So that simplifies our expression. So now we have delta E equals Q. And because we're at constant volume, we're just going to put a lowercase v there. Another way we can see this formula is delta E equals our heat, again, over a mole. And so I gave a table here just so that you can compare and contrast. Like I said earlier, we're not going to be looking at, this is again on this side, our coffee cup calorimeter. So we will do that later. But here are the conditions for our constant volume. This again is our bomb calorimeter. So let's go to the next page, and I'm going to show you what a typical bomb calorimeter looks like. Let's go over here. So here, let me straighten out my pages. Here's our bomb calorimeter. Calorimeter. Okay, so what do we have here? So this is going to be, it's usually metal on the outside. And what do we notice here? This is a chamber. So this is a combustion chamber. A combustion chamber. Okay, and then usually we have a thermometer that we could read here. There's a stir. So back in the day when I was a student for a class, I actually measured potato chips, and I wanted to see if the manufacturer was being honest about the calories in the potato chips. So I combusted some Lay's potato chips, and it was, after doing the calculations, it was pretty spot on. So they were not lying. So here, by this vessel, well, we can see that the volume of our calorimeter doesn't change. It's not going to change. And the total energy changed itself through heat only. Through heat only. So we're measuring the heat by how the temperature of our calorimeter changes, and that's why we need this thermometer. So there's a few formulas that we should write down. So our minus Q of our reaction, so we're combusting whatever we're looking at here in that chamber, is going to be equal to the positive of our heat of our calorimeter. So the heat lost by a reaction is going to be gained by the calorimeter. And then we also have this formula, our minus Q of reaction. Our minus Q of reaction is going to equal our Q of calorimeter there, again, but our calorimeter is going to be our heat capacity, C, times delta T. So you guys hopefully remember the big C was heat capacity. Heat capacity. So let's take a look at a typical problem. So in this example, we've got 6.55 grams of aniline, its molar mass, and it was used in the bomb calorimeter. They combusted it. If the temperature rose by 32.9 degrees C, use the information below to determine the heat capacity. So what are we going to solve for in this problem? Well, what we want to solve for is the heat capacity. So we need to find our heat capacity of our bomb calorimeter. So that's what we're trying to find. Now, what's given? What's given is we know our delta T, it rose, so that's our change, is 32.9 degrees C. We're given a mass, 6.55 grams of aniline. And we're given something different in this one. Delta H of our reaction, which is minus 1.28 times 10 to the 4 kilojoules. Well, delta H, we're going to learn more about this later. After you're done with all the modules, this part will make more sense. But this is called the enthalpy. There's another name, but for now, let's just call that the enthalpy. Well, it's also heat of reaction. But here, just notice the units. It's an energy again, right? So we've been using joules this whole time. Sometimes you can see this in calories. So we're going to have to do some stoichiometry with this problem. So it gave us an equation, and it gave us our enthalpy. Now, what other formulas do we know? We know, or the relationship, we know that the heat lost by the reaction is going to be gained by our calorimeter. And we know that Qcal is going to be equal to our heat capacity times our delta T. So I'll just keep calling that the heat capacity of our calorimeter. So what should we do first? Well, to find our heat capacity, this symbol, what do I have to know? I have to calculate our heat. Well, our heat of reaction is given here, but I can't just plug that in directly because I have a mole-to-mole relationship between my reactants and products, right? So let's go ahead and look at this first. So we've got 6.55 grams of C6H5NH2, and I know we've got 93.13 grams in 1 mole. So now I want to begin talking about this delta H of the reaction. When they give us delta H, this minus, for those of you wondering, this is exothermic. So we talked about it a little bit in lecture, and I'll say we're going to come back to this. This is exothermic. So that's going to be, it's giving off heat, which should make sense. It's a combustion reaction. But why did I have to go through grams to get to moles? Well, I have a specific relationship with this heat of reaction. I've got 4 moles of my aniline per this amount of kilojoules. So that means I've got 4 moles. So if this was a 3, you would have to put a 3 here. So basically you're using a conversion factor here. So you've got 4 moles to what? Well, the total energy here given off is 1.28 times 10 to the 4 kilojoules. So moles cancels, grams cancels, and we're going to be left with negative 225.06 kilojoules. Now again, I wasn't able to show you this in class, but I'm doing a whole module just on this topic. But for now, realize that if I was looking for NO2, I would have 4 moles compared to my minus 1.28. Now, if I was looking at water, I would have 14 moles per minus 1.28 times 10 to the 4 kilojoules. So now we have Q. So all of this process was to get Q. So this is Q of our reaction. Now don't forget our relationship. Our relationship is minus Q of our reaction equals Q of our calorimeter. So this is a negative if it's my Q of reaction. So I need to find our heat of our calorimeter. I need to make this positive because it's actually gaining that amount of heat. So I have this amount of heat. Now what could I do? Well, I still just need to find our heat capacity, but I have our Q cal. So, and I have our delta T. So now I can set up the formula. So let me set it up like this. Q cal equals our heat capacity for our calorimeter times our delta T. Well, we know this is 225.06 kilojoules. We know our delta T is going to be, what was it again, 32.9 degrees C. So if I want to solve for my heat capacity, I'm dividing both sides by 32.9 degrees C. So I will now, if I solve this cancels, and I will get 6.8 kilojoules per degree C. Okay, so hopefully this made sense. And I can, if you have questions, we'll use Zoom for office hours and you can ask me then. But in this module, you're also going to be given a similar problem to practice. Okay.